So here in lecture 8.5, we're going to complete our treatment of don't cares in multi-level logic and how they arise implicitly from the structure of Boolean logic network models. The final class of don't cares are the observability don't cares. Observability don't cares are patterns that mask the output of a node so that no matter what happens, the output of the overall Boolean logic network is insensitive to your node when this value shows up. So these are different than the controllability don't cares, which kind of focus on the nodes in front of a node. The observability don't cares focus on the nodes in back of a node between you and the output. But it turns out that the same computational Boolean algebra techniques we learned at the beginning of class will let us come up with a recipe to extract the don't cares. So let's go look at the observability don't cares.
So here we are finally at the last kind of implicit don't cares. We've done the satisfiability don't cares and the controllability don't cares, and now we want to talk about the observability don't cares. These are patterns input to a node that make the network output insensitive to the output of the node, or patterns that mask the output from affecting anything. Let's see how we compute these. So I've got a new benchmark here, got a new example. It's got 3 primary inputs A, B, C, and 1 output Z. The node F that we want to optimize is now in the middle of the network. It's interior to the network. It goes through a node Z equals AB plus F C bar plus F bar B bar in order to get out. So observability don't cares are patterns that mask a node's output, and in our case this is F, at the network output, which in this case is Z. So, it's a really important point here. These are not impossible. These patterns can occur. But these patterns make the node's output not observable at the network output. And what that means, not observable, means that the Boolean value of the node, in this case F, does not affect any network output, which in this case is Z. So it doesn't matter what F is. Z doesn't care. So it's a real don't care in a different kind of a way. So, just to be clear, the observability don't care for F is going to be patterns of A and B, because that's what's input to F, that make Z insensitive to F's value. Let's just go talk a little bit about that insensitive thing. When is the network output Z insensitive to the internal variable F? And note that we've got 2 nodes here in my kind of cartoon. There's an F equals stuff node with some arrows into it, and that has an arrow labeled F that goes into a Z node that says Z depends on F, and Z has some other arrows going into it. What it means for Z to be insensitive to F is that Z is independent of the value of F given some other inputs to Z. We can be clear about that with some little examples. So for example, if Z was just an AND gate, if any other input was a 0, Z is insensitive to F, because if there's a 0 going into the gate, Z's just a 0. Similarly, if Z was an OR gate, Z would be insensitive to F if any other input was a 1, because if any other input is a 1, Z's just a 1. What we need is a general formula. We know that Z depends on F. How do we compute in the general case when Z is insensitive to F? Now it turns out we've almost seen this before. We solved the flip problem. What makes F sensitive to X? Now note the change of variable names here. This is a blast from the past. This is slide 21 of lecture 2.6 that talked about the Boolean difference. And what that said was that any pattern del F del X equal 1 makes X observable at output F. So interpreting the Boolean difference, we have a box that says a big blob of logic, and has an output that says F is a function of A, B, C, dot, 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 W, and X. And there are arrows going into the big blob of logic that say A, B, C, dot, 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 W, and X. And what the slide says is that any pattern of the other variables that are not X that makes del F del X1 makes F sensitive to X. And the words say when del F del X is a 1, it means that if you apply a pattern of the other inputs, A, B, C, up to W, that makes del F del X 1, any change in X will force a change in the output of F. So we know what makes some output sensitive to some input. We just want the opposite. We want the output to be insensitive to the input, which is going to turn out to be easy. When is the Z output, which is the output node in the diagram here, insensitive to the F input because F is an internal node? Well, the slide title gives it away. It's when the Boolean difference del Z del F complemented is equal to 1. That makes sense. Let's talk about that with a little bit more detail. When is the network output Z insensitive to internal variable F? Here's a good mathematical definition. When you can find some inputs to Z that make the cofactors Z with F set to 0 equal to Z set to F equals 1. So if ZF equals ZF bar, the Shannon cofactors, then Z is not dependent on F. Any inputs to the Z function that make ZF equals ZF bar make Z independent of F. If the cofactors are the same, when you set F to 0 and F to 1, Z does not depend on F. That makes sense. How do you find when the cofactors are the same? Well, you solve a little equation that says, I'm going to put an equality gate, and that's an exclusive NOR, in between the two cofactors, ZF equals 0 and ZF equals 1, and I'm going to solve for when that's a 1. Now note that Z exclusive NORed with ZF of 0 exclusive NORed with ZF of 1 is just the same thing as ZF of 0 exclusive ORed with ZF of 1 and complement the whole thing. So that's nothing, complicated. That's just the difference between an XNOR and an XOR gate where you just put an inverter after the XOR gate. But the reason I wrote it like that was that this is sort of familiar. The thing under the big bar, ZF equals 0 exclusive or ZF equals 1, is just the Boolean difference. And so I finally get the result I want. If you can compute del Z del F and then complement it and then find a pattern that makes it a 1, and then take that pattern or those patterns and apply them to the other inputs to Z that are not the F input, any pattern that makes that thing a 1, del Z del F bar, any pattern that makes that a 1 makes Z insensitive to F. Those patterns are the raw material of the don't care that I need to go compute. So I have a recipe again. It looks a lot like the previous recipes we've seen for the don't cares. What do I start with? I start by computing del Z del F complement. Any patterns that make that thing a 1 mask F for Z. Make Z not depend on F. And then I universally quantify away all the variables that are not inputs to F, because just like with the controllability don't cares, there's a lot more variables happening here, and the patterns of behavior that I'm interested in must stay true for all values of the variables that I get rid of. And the result will be the observability don't care is a Boolean function that makes a 1 for these masking patterns. So here's the equation. I'm again showing you the same network. F is AB bar plus A bar B, feeds Z is AB plus FC bar plus F bar B bar. Z is the primary output, ABC the primary input. Circling the inputs to the Z node, the output don't care, okay, is something that we compute starting with this raw material, okay. It's the universal quantification of the variables not used in F applied to the complement of del Z del F. And then what that's going to do is that's going to let me actually go over and get some patterns that are don't cares for the F node. So using this recipe for the little network, F equals AB bar plus A bar B, Z is AB plus FC bar plus F bar B bar, what do we get? We look at all the variables going into Z. We calculate del Z del F bar, and then we calculate the universal quantification of the variables not used in F, and we get some patterns to the input of F. That's going to turn out to be for all C, because those are the patterns, those are the variables that are not used in F. A is in F, B is in F, but there's no C in F. Of the complement of the Boolean difference. So the Boolean difference is just AB plus FC bar plus F bar B bar, cofactored F equals 1, exclusive OR, cofactored F equals 0. That's the difference. Then you complement it, and then you quantify out the C. If you do that, you will be quantifying the C out of the Boolean equation AB plus AC bar plus B bar C bar plus A bar BC, and when you're done, you get something useful. You get some patterns that you can actually apply to the inputs of the node that you are trying to simplify. So that's the computational recipe so far for the output don't care. Now, as we did in the previous CDC example, it's good to just ask the question, does this make sense? If I tell you that the ODCF, which is a function of A and B, is AB, that means that we think A equals 1, B equals 1 masks F from affecting the Z output. Is that the case? Well, if A is 1 and B is 1, then the AB term in Z turns into a 1. And very clearly, it forces the Z output itself to be a 1. And once you force the Z output to be a 1 with A equals 1, B equals 1, Z doesn't depend on F anymore. So yes, in fact, A equals 1, B equals 1 is a don't care for node F. It all works because A equals 1, B equals 1 forces Z to be a 1. And if you actually look at F, what you can see is that F is actually AB bar plus A bar B. F is actually an exclusive OR gate, right, before we did any of the don't cares. And after we find this don't care pattern, which is A equals 1, B equals 1, what we're actually going to find is that we could, if we choose, we could replace F as an OR gate, because now 1, 1 is something that's a don't care pattern. We can circle it if we like. And we can decide if an OR gate is simpler than an exclusive OR gate, which is probably true. Then in logic, in actual silicon, then this is probably a good simplification. So that's what you actually get from this particular don't care pattern. Now, we're not quite done yet. We have a new problem. What if F passes through many outputs and is an input to many Z nodes, Z1, Z2, dot, 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 Zn, each of which make a primary output? Well, the big idea is that only the patterns that are unobservable at all of the outputs can be observability don't cares, because as soon as F affects even one of those nodes, then it's not masked, and I can't make it a don't care. I have to be careful that I compute the right value. So I get a formula that looks much more like the controllability don't cares. So the general recipe for the general ODC is, again, you quantify away all the variables that are not input to F, right? Because that's what we're working on over here. But what you quantify is the Boolean AND of all of the complemented Boolean differences. So you take all the Z's, you calculate the Boolean difference, you calculate the complement of the Boolean difference, you AND them all together, okay? And you quantify away the variables universally that don't show up in F, and then you solve for, ones in this. Any pattern that makes that thing a 1 is an observability don't care. It makes F unobservable at all of the Z outputs. And that's the recipe. So, where are we with the ODCs? ODCs give patterns input to node F that mask F at the network output. They are not impossible. They can occur. Don't cares. Why? Because the network output doesn't care what F is, because F does not affect the network output for these patterns. The ODCs can be computed mechanically from the Boolean differences of all the outputs that are connected to F. Together, the CDCs and the ODCs give you the full don't care set you can use to simplify an internal node. With these patterns, you can call something like espresso and simplify the insides of the sum of product form for the node. Now, a really good question at this point would be, are we done? I talked about satisfiability don't cares, I talked about controllability don't cares, I talked about observability don't cares, and the answer is yes, but only if your networks look just like this. And just like this means you have one layer of inputs in front of F, x1 to xm, and one layer of outputs in back of F, z1 to zn, that generate primary outputs. So if you only want to get the controllability don't cares from the nodes immediately before you, and you only want to get observability don't cares for one layer of nodes between you and the output, then all of the math and all of the recipes I've given you are all you need. Unfortunately, this is what a real network looks like. And so here on this slide, in general, I'm showing you X, which is in the middle of a large network. And so there's several ranks of nodes with many nodes at every rank feeding X, and several ranks of nodes with many nodes at every rank between X and some number of primary outputs. And the problem is that controllability don't cares are actually a function of all of the nodes in front of X, potentially. And observability don't cares are a function of all of the nodes between X and any outputs that it might influence. And in general, this is so complicated that you can never get all of the don't cares for node X in a really big Boolean logic network. And even just representing all this stuff can be explosively large, even for BDDs. So what do people actually do? Well, they generally don't get all of the don't cares. There are an enormous number of tricks that trade off some effort in time and computer memory for quality for how many don't cares. So for example, the formulas I gave you for the controllability don't cares, the so-called local controllability don't cares, which requires that you just look at the outputs of the nodes in front of you, the immediate antecedent vertices, the nodes in front of you, and you compute those satisfiability don't care patterns. That's a really common trick, and that works pretty well. There are also incremental node-by-node algorithms that walk the network from the inputs to your F node to compute the controllability don't cares, and from your F node through layers of nodes to the output Z's to compute the observability don't cares, but they're just more complex, and I don't have enough time to talk about those things. The references that I gave earlier in the lecture are a really good source for those algorithms. But for us, just knowing these limited don't care recipes is actually sufficient. You now understand why don't cares are implicit. You understand why you must find them. You understand how you can find them for a nice, pretty realistic case. And you know the big difference between the satisfiability, controllability, and observability don't cares. This is great. You're really in a very, very good position now to understand pretty much most of what happens in the sort of a core version of conventional logic synthesis. So congratulations. Lots and lots of progress. What we're going to be doing next is moving on toward more physical layout kinds of problems. Because remember, the title of the course is From Logic to Layout. We're almost done doing all the logic stuff. We're about to move into the layout stuff.